Okay, so I'm going to start now. Good afternoon, everybody. I'm going to talk today about energy efficiency in the transportation sector, and I'm going to focus on hybrid vehicles. Okay, it's a very important subject in terms of energy demand, as you will see in a few moments. Okay, so regarding energy efficiency and energy use in the transportation sector, the problem, and you will see during the class today, that this subject is a very multi-branched subject. It's impossible for me to cover all these subjects in a single class, a 3 hours class. So I decided to follow some branches as I'm showing you here. So hybrid cars, as I already mentioned, is one end point here in this multi-branched tree. Okay, but I'm not only going to talk about hybrid cars. Sometimes I'm going to talk about aviation fuel, for instance, which is a completely different subject compared to hybrid cars, and it belongs to another branch. So I decided to show some specific points like jet fuel and hybrid cars. And that means that sometimes I'm going back on this tree and going forward in order to change the end point, okay, of this subject, of this whole subject. So forgive me if sometimes the class appears as I'm showing you here, multi-branched. I'm going forwards and backwards, but that's a main characteristics of this area here, okay? So just to give you a big picture, we are returning to our Sankey diagram of the energy use, and as I already mentioned, this regards the United States, but it's very representative of the world energy consumption, divided in terms of energy source and end uses of energy, and in the middle we have the carriers, or vectors, as we say in Brazil. So, for instance, when we talk about electricity as a specific vector, I already showed you that most part of the electricity is generated from coal and natural gas, and this is transformed into electricity through thermal power plants. Okay, so this orange segment here corresponds to electricity, and it goes to residential applications, commercial applications, industrial, and I don't know if you managed to see a very tiny line here going to the transportation sector. And what I wanted to emphasize here is the great amount of energy that is actually lost. This gray segment here is rejected energy. This is mostly related to the efficiency, the second law efficiency. Okay, it's impossible, as I already mentioned, not to reject some amount of energy. This is due to the second law of thermodynamics. In terms of transportation energy use, you see that electricity is a very small amount. Okay, because it basically uses liquid fuels as an energy carrier or energy vector. Okay, so basically it's petroleum, okay, that is transformed into gasoline, and we have the same problem here as in the electricity generation. You are bounded by the second law of thermodynamics, so just a small amount becomes actually exergy, or useful energy. The rest is lost due to implications of the second law of thermodynamics. So we're going to look into details here, this flow from the energy source to the energy carriers or energy vectors to the application. Okay, we're going to talk about all this. And when we open, I'm going back one slide here, or actually here at the input of the transportation sector, you see all kinds of energy vectors gas, fuel, okay, diesel, gasoline, other liquids, ethanol is here, for instance, and electricity. You can see how this is divided in terms of the what we call modal, transportation modal. You see, for overseas transportation, you can use diesel engine here or other liquids. For instance, heavy oils that you burn in very big burners that you can build in a big ship, but it's not applicable in, for instance, for light road applications. Okay, so if we follow gasoline here, for instance, gasoline, you see that it basically is used for light road transportation. Okay, the numbers are here in terms of exajoules, and well, this is mostly to passenger transportation, and that is the amount lost and the amount that actually is transformed into useful energy. Okay, and why is that? Because gasoline burns on spark engines. Okay, as we say, they use the Otto thermodynamic cycle. Okay, and the problem is the flame propagation speed. If you have very big engines for a ship, for instance, you cannot use Otto cycle engines. You have to use diesel cycle engines or even other liquids here. Okay, so the characteristics of the engine that is transforming the energy content of the energy vector to useful energy or exergy, it determines somehow the type of fuel that can be used in that particular application. Okay, you see, for instance, another point here is electricity. It's basically used for rail transportations, okay, for trains, okay, and the amount lost here is actually virtually zero because electricity is a pure exergy. So you don't have a conversion limited by the second law of thermodynamics as we have for these types of application. Okay, so this is the big picture concerning the transformation of the primary source of energy, okay, to mechanical exergy, which is actually kinetic energy, okay, when we talk about the transportation sector. Moving forward, another point here is that when we talk about energy efficiency, you have to specify in terms of what. Also, this is a very multi-branch subject, and we're going to focus on two aspects of energy efficiency. We're going to focus on in terms of energy demand per modal of transportation, okay, and also in terms of greenhouse gases emissions, okay, or as we say, the environmental cost of that transportation technology working or using a particular kind of fuel. Okay, we're going to focus on those two subjects during the class today. Still in this big picture, let's talk a little bit about the historical content and geopolitics of energy regarding the transportation sector. As I showed you, the amounts in terms of the amounts of fuel, okay, gasoline 38%, so this is mostly for small vehicles actually. By small I mean less than 200 HPs, horsepower, okay, so this is small. Diesel engines for bigger applications, and let's say very, very big applications you can also use. Kerosene for aviation, okay, and you have a bunch of other types of applications. And you see that when you talk about renewable energy sources, you may have some amount here, other liquids, so ethanol enters here in other liquids, and electricity, depending if this electricity is generated from a photovoltaic power plant, for instance, or from wind. Okay, so depending on on the primary source of electricity generation, you can say that a small amount of renewables are entering here. So you see that basically the whole world is running, in terms of the transport sector, with fossil fuels. So that's a very important problem. I already mentioned, okay, this in our first class, that the anticipated decline of the world's petroleum and gas production, according to Hubbert's law, have been proven premature. Okay, so we expected, I would say 10 years ago, that these fossil fuels would be very expensive today. Okay, and this would enable the other fuels produced from renewable sources. This did not happen. Okay, it may happen in some years, I don't know, but this is the scenario today. Another important point is that renewable energies or renewable sources compete economically and technically with fossil fuels. I'm going to talk a little bit, elaborate on this subject in a few slides, because it partially explains why renewable fuels are having a hard time displacing fossil fuels, because of this competition, economical and technical competition. Okay. Another important point is the concept that we refer to as drop-in, because in addition to competing in terms of price, biofuels must adapt to the existing infrastructure developed originally for petroleum products. Okay, so if you're producing ethanol, for instance, and you want to send a very large amount of ethanol, let's say 2,000 kilometers away, you may be thinking it would be interesting to use these pipelines for petroleum. But the problem is that these pipelines were built for petroleum products, gasoline and so on. So it's not directly applicable. You have material problems, for instance. Ethanol tends to be corrosive when you apply it to these pipelines built for gasoline, for instance. So the material, the pipeline, is not adapted for ethanol transportation. Okay? So that's one kind of problem that you have related to this drop-in concept. That is, you have to use the same infrastructure. You're not going to build an alternative infrastructure just to transport ethanol, for instance. You have to use the same infrastructure. And also fossil fuels or fossil sources will continue to be exploited, with consequent intensification of CO2 and other greenhouse gas emissions. And this is because I already showed you there is a lot of, a very big amount of oil and gas as reserves, proven reserves. By proven, I mean they are viable in terms of economicity. Okay, one very interesting example is Venezuela. Okay, in Orinoco Bay, you have another Saudi Arabia waiting to be exploited in Venezuela. Also, I'm sure you heard about shale oil and shale gas in the United States, and also about these sands in Canada that they also have a very big amount of oil. Okay, so this is the amounts are big. They are cheap, they are viable, because now we have technology to exploit these reserves, and it is possible to anticipate that these fossil sources will continue to be exploited. Okay, so that's the problem, okay, that we have. And this point here, that fossil sources will continue to be exploited, puts some importance in CCS techniques. Okay. Because these emissions will intensify. Okay, moving forward, let me try to characterize the whole sector in a graph. That's very very hard to do, but I'm going to try. Okay, so if we talk about what we call operation envelope, in which we are going to try to map, to characterize all these transportation models. Okay, this operation envelope we can define in terms of the energy cost and the velocity. Why? Because when you want to transport something from point A to point B, what do you want? What would be the ideal situation? You go as fast as possible, so you go to the right hand side here of this axis, and consuming the smallest amount of energy as possible. So actually in this graph you want to operate in this region here, okay? That's the best possible situation. You're going very, very fast and spending very small amounts of energy. This is the ideal situation. In this graph, we're going to plot in terms of what we call normalized energy cost. Okay, I'm not too sure. I think it's a passenger's car. Okay, traveling at 30 meters per second. It's more or less 100 kilometers per hour. Okay, this specific consumption, we're going to say that it is 1. Okay, so how do we construct this graph? We go to all, we get the data sheets of cars and airplanes and all types of transportation, and we make the calculations. What's the average traveling speed? Okay, so if we're talking about a jet airplane, probably the airspeed is going to be 1,000 meters per second, the average transportation speed. And what is the consumption of this airplane, for instance, okay, in terms of kilograms of kerosene per second, okay, and then we divide this by our reference transportation, which has the energy cost normalized to 1, okay, and we're going to do this in terms of freight transportation and passenger transportation, okay. So when we do this, we get, for instance, in terms of passengers, you see jet airplanes, turbofan airplanes, well, supersonic airplanes we don't have anymore in terms of commercial airplanes. This was the Concorde, the French Concorde, and also the Russian Konkordsky, okay? They are not operational anymore, but commercial airplane, okay, commercial transportation companies work with turbofan airplanes, so it's more, the corresponding speed is more or less 300 meters per second, okay, and the normalized energy cost is around the unitary cost, which corresponds to a bus or a car, a specific bus or car, okay. You see turboprops also. They travel a little bit slower, but they can be much more efficient in terms of energy. I think I already showed you this. Okay, a helicopter has a very high energy cost and a low traveling speed compared to other airborne transportation technologies. Okay, cars. By cars, I mean passenger cars, individual cars, okay? Buses, trains, and, well, bicycle here, just to give you a reference. So, bicycle consumes a lot less energy. Okay, an observation, this is a log scale, okay, in terms of energy. So, bicycle is roughly 10 times, spends 10 times less energy, but travels much more slower. Okay, when we put transportation, freight transportation, okay, you see similar things. In general, you tend to work to the left here because you're not so concerned about speed, but you're more concerned in terms of energy because this is going to be transformed to cost, to money. Okay, so you see turbofans for transportation or freight. Okay, road trains, this is for trucks. Okay, so buses and trucks becomes road train. Oh, here gas pipelines, oil pipelines, sorry for the Portuguese in this slide, okay? And ships, container ships, and tanker ships for transportation of liquid products. The point here in this graph is that I mentioned that the idea would be to work here in this region. And you see that there's a void here. You don't have all these regions here correspond to actual applications, okay? So those are data that you get from the suppliers. If you want to buy an airplane, you go to Boeing and ask for the speed and consumption, and you get a point in this graph, okay? So these are actual data. They were compiled by these people here, okay? And my point here is that you get a void. You see that there's a void here. Why is that? Why there's a void here in knowing that this would be ideal to work here? This reflects, actually, I'm going back a few slides. This reflects, here, this situation here. You get useful energy, but you have a lot of waste energy, okay? And this is impossible not to reject some amount of energy due to the second law of thermodynamics. So this is a manifestation of the same problem, okay? This void here is a manifestation of this efficiency. It's impossible to travel very fast and consuming very small amounts of energy, okay? You don't get something for nothing. So there is a void. This is a natural. It is natural that you have a void here. It's a consequence of conservation of energy, but also of the second law of thermodynamics. And these, you can also identify, in addition to this void, you identified a kind of a frontier here, okay? This frontier actually works as a Pareto frontier, okay? That means that there are some transportation technologies that are already optimized in terms of energy cost and speed, okay? So it is possible, possibly it is impossible to get better than this situation here, okay? So you see already in terms of airplanes for passengers, okay, the tendency here is to become very, very big. Why is that? Because the main influence on the cost, operational cost of this machine here is drag, aerodynamic drag, which is, so drag is proportional to, let me write this down, okay? So the drag force is proportional to the external surface area of the airplane, which is proportional to the square of the scale factor, okay? And this represents cost, okay? Cost. The amount of revenue that you get from this machine is proportional to the internal volume of the aircraft, okay? Which is proportional to the scale factor to the third power, okay? So when you increase the scale factor, okay, S, here you have costs and revenues. You see that when you increase the scale factor, costs increase slower than revenues, okay? So this is C, this is R, and this would be something, let me change a little bit here, and this is money, okay, value. So you see from this situation here that the bigger in terms of scale, the better, because you're going to get more revenues compared to the increase of cost. And so that is why you have bigger and bigger airplanes. You also have bigger and bigger ships, super tankers like this one, and super containers like this one, okay? And you also have, in terms of road transportation, what we call road trains. Here in Brazil, we already have 2 or 3 wagons, but in some places, as in Australia, for instance, you may have 10 or 12 wagons in this truck here, okay, being pulled by the truck here. So the tendency is mostly explained by this situation, okay, and the fact that we already have very big airplanes and very big trucks and very big ships is related to this limit, multi-objective limit here, or what we call Pareto frontier. Okay. So the point is, given this scenario that I just depicted to you, the question that arises is this one: will biofuels displace fossil fuels in the transportation sector, or what it takes for biofuels to displace fossil fuels in the transportation sector? Okay, so we're going to elaborate this question along the class today, and as I mentioned in the beginning, it's a very multi-branched subject, so I'm forced to sometimes to focus on specific points, sometimes to take a few steps back in order to focus on another point. Okay, we're going to try to elaborate this during the class. But first, another guideline of this class or this strategy is the saying by Sun Tzu. Okay, The Art of War. He published this book, and there are some points here that I want to emphasize. He's saying is that if you know the enemy and yourself, by enemy I mean fossil fuels, and yourself renewable fuels. Okay, so if you know the enemy and yourself, you need not to fear the result of 100 battles. Okay, if you know yourself but not the enemy, so if we know a lot about biofuels and renewable fuels but nothing about fossil fuels, for every victory gained we will suffer defeat, okay, because you don't know things about petroleum, okay? And if you know neither the enemy nor yourself, you better go home, because you will lose every time. So I'm going to try, that's a very comprehensive subject, I'm going to try to be here, to satisfy this, to show you, to talk about ourselves, I mean, to talk about renewable fuels, but also I'm going to talk a little bit about fossil fuels. Okay, I'm going to try to accomplish this. So, will biofuels displace fossil fuels in the transportation sector? Well, let's see the transportation sector. So, how is the scenario today? So we have, in terms of applications, okay, we have motorcycles and small vehicles, I would say, okay, 23%. This is basically gasoline or ethanol. So if you want to produce renewable fuel, you have to look at the application. So for the auto cycle engine, you may produce ethanol or something similar that runs in a spark ignition engine, okay? Or you can try to produce kind of a biogasoline, okay? But you can also use this fuels for light trucks. But for heavy trucks and other heavier or bigger applications, you're going to have to produce some kind of diesel or fuel for the diesel engine, okay? So heavy trucks, 23%. Aircraft, aviation fuel, that's a very important application. It's only 8% in terms of the total here, but it is a very specific application. I'm going to elaborate. I'm going to show you what it takes in order to produce a renewable source for this kind of application. It's a very, very, very interesting challenge here. Okay, so you also have ships and so on. Okay, so we want to, let's say, produce fuel for auto cycle engines. So it's a very interesting possibility, okay, ethanol or biogasoline or something similar, okay, but we also need to produce diesel for bigger engines. So there are some points that I want to emphasize related to these questions. First, diesel engines, as I already mentioned, or diesel engine biofuels for high power engines greater than 1,000 horsepower, are still in the early stages of deployment. okay, mainly due to feedstock issues, because we don't know, we don't have a good source of lipids actually in order to produce biodiesel. We don't have a good source of lipids that does not influences food prices, for instance. So if we make biodiesel from soybeans, it's going to somehow to connect to the price of oils used for cooking, for instance, or for the production of animal feedstock also. So you see that this is not desirable actually. Okay, you let these communications happen. Okay. Another point is that biokerosene for the Brayton cycle. Okay, so these engines run based on Brayton thermodynamic cycle, is still in the process of technological development associated with its certification as an aviation fuel. I'm going to show you this, the conversion routes, and also what it takes to certify a specific biofuel for aviation application. Okay. Another point is that industrial processes of biomass conversion to biofuels for auto engines must evolve to TRL 8 to 9. We have already, I mean, second generation ethanol here, okay? Mostly. This statement relates to second generation ethanol. Because here in Brazil, we have, in Brazil we have a very mature industry, first generation ethanol production. It's very mature. It's certainly TRL 9, but in terms of global applications, you cannot scale that up. Why is that? Because you don't have sugarcane everywhere in the world. Okay, so you need, in terms of global applications, you need a source of biomass to produce bioethanol, for instance, and this is basically based on second generation technologies. Okay, agricultural residues and so on. So it's still, we have some applications I already showed you, but they have well, they have to mature a little bit more because they are not competitive in terms of their economicity. Okay, and also in terms of robustness of the process of the machines and equipments and processes related to the second generation bioethanol production. They are not as they perform adequately, but they are not as robust as the equipment for the production of gasoline from petroleum, for instance. Okay, so you still have some technological development to do in this point here. Okay, and finally, the overall economicity must be improved by integrating new technologies to enable larger scale systems. So that's another point. When you compare gasoline from petroleum, when you compare that with ethanol, for instance, you see that the characteristics of petroleum are so that you may have very, very, very big refineries and applications, so you can benefit from economies of scale. That's not what happened with ethanol, because you cannot upscale to that point, because you're limited to what we call the agro-industrial system. I already showed you this. Okay, so ethanol production will be always based on small refineries compared to petroleum refineries. Okay, and these small refineries are spread on the cultivation area. Okay, and this is because basically because of the costs associated to harvesting the production and taking this biomass from the fields to the central industrial unit. So these costs actually limit the size of a biorefinery based on agricultural feedstock. Okay. In terms of emissions, when we compare these applications, all these ones, This is grams of CO2 per kilometer, okay? You see that bicycle and walking it's fantastic, yeah? But, well, you know, you go very, very slow. Airplanes are terrible. That is why this 8% is actually very important, because this 8%, this number here, is in terms of energy consumption. But in terms of CO2 emission, you see that, well, it's at least 4 times the second worst one, which are those small cars, okay? So this 8%, you may multiply it by 4, roughly speaking, in order to assess its importance in terms of CO2 emissions. So that is why it's very important to develop a biofuel for jets, for aviation, okay, because it's very intensive in terms of CO2 emissions. So the second worst one is cars, and then hybrid car. I'm going to talk about hybrid cars today, okay? I'm very fond of this technology because I think it combines the best in terms of internal combustion engine and the electric drive. Okay, it combines the best of these two technologies. Also trams and metros, okay, city buses and regional buses, trains and high-speed trains and so on. So you see this graph here is here just to show you two to justify what I'm going to focus further on, because I'm going to talk a little bit about this problem here, what it takes to produce and to certify an aviation fuel, okay, based on renewable feedstock, and also I'm going to talk about hybrid cars, hybrid and electric cars in terms of a substitute for these cars here, okay? These cars are obviously, they are not electric cars, they are internal combustion engine cars. So this justifies a little bit the importance of talking about aviation and also hybrid cars in a few moments, okay? Well, talking about biofuels for the aeronautical applications, first of all, I want to say that there's a very good report published by FAPESP. If you just type this title here in Google, for instance, you get the link to the PDF, so you can download this report. And there's a lot of very interesting information, okay, in this report. And most of the information that we have in the following slides come from this report here, okay. Another point that I want to emphasize is that, well, we already tested biokerosene in an airplane. The story of this test is very interesting. The complications associated to this test is very interesting, because, you know, one of these engines was running with biokerosene, and the other one was running with traditional kerosene, aviation kerosene from petroleum. Okay, and this is so because some problem happened with this engine here. You still had the other to move the plane. Okay, so the story is told here, but I want to emphasize it. And another point that I want to put right now is the drop-in related problems. When you develop this aviation fuel, biofuel, you have very significant drop-in problems. Okay, so I'm going to talk a little bit right now. Okay, in terms of technical specifications, when you compare, for instance, comparing gasoline for cars with kerosene for airplanes, the corresponding technical specifications for the aeronautical applications are very, very, very tight. Okay, very detailed, and well, we have very severe specifications, because the applications, the environmental conditions that an airplane can encounter during its operation varies a lot. Okay, in terms of temperature, for instance, you may be at 50 degrees if you are parked in an airport in Saudi Arabia, for instance. This fuel may maybe feeling 50 degrees Celsius, and 30 minutes later at 10,000 meters high, this same fuel may be at minus 20 degrees Celsius. So the conditions are very harsh, and that is why the technical specifications are very tight. Okay? In terms of heating values, for instance, the heating value of an aviation fuel, a generic aviation fuel, must be higher than 42.8 megajoules per kilogram. This is very high. This is methane, for instance. Pure methane is something like this, the heating value. So it's a very energy-intensive fuel. Okay, so a very powerful fuel in terms of energy content. The density is also high. It's a little bit lower than water, but still very high when compared to natural gas, for instance. Okay, natural gas is roughly speaking, is 1 kilogram per cubic meter at normal conditions, and the density of a jet fuel must be close to a little bit smaller than 1,000 kilograms per meter. And why is this? Because, well, the space, one of the most valuable things in an airplane is space, volume. So you need to carry a lot of kilograms of fuel, okay, and spending very small amounts of cubic meters. So you have to have density. I mentioned natural gas, methane, okay? Methane has a very high energy content, but a very low density. So it's impossible to make an airplane, to run an airplane with methane, because the size of the reservoir would be prohibitive. Okay, so that's another point. But also, it has to have an adequate volatility. Okay, what I mentioned, the freezing point must be smaller than minus 47 degrees Celsius for this type of aviation fuel. I'm going to show you the different types. Okay, viscosity. This is a specification related to the already existing equipment. So the viscosity at minus 20 degrees must be smaller than 8 square millimeters per second. Okay, and why this is so? Because you already have pumps and pipelines in the airplane that runs with kerosene, petroleum kerosene, and well, if you want to use the same equipment, you have to comply with this specification. Okay, so this is a very typical of infrastructure, using the same infrastructure, in this case, the same fuel pump, the same pipelines, the same reservoirs, and so on. Okay. Another point, no presence of water. As I said, it's going to experience very low temperatures, so you cannot have water. It also has to be chemically stable and low corrosive potential. Okay, and this, this is relative to the existing reservoirs, okay, and infrastructure. And for more details, I would say all of these aviation fuels must comply with IATA and ASTM specifications. Okay, so those are technical specifications. I just added one here. I'm going to show you a lot more. So this is simply some examples, but the whole specifications are defined in these norms here. Okay, let's move on and see what is the process. I'm trying to condense here in one single slide all conversion routes. Sorry for the Portuguese, but it's from the FAPESP's report, so that's why it's still in Portuguese. So in this slide, I'm going to show you the possible conversion routes from the feedstock to the final aviation fuel. Okay, so I'm going to show the conversion routes and the related technologies. Also, the specification that a specific conversion route has to satisfy. Okay, and also the types of tests that you have to pass in order to qualify for this type of application as an aviation fuel. So let's for instance look at, let's see, production of aviation fuel from starch. Okay, from starch. Okay, so yeah, first I forgot to mention something. We have roughly speaking 3 families of conversion routes: thermochemical conversion, okay, biochemical conversion, and lipids conversion, which is actually a thermochemical route, okay, but it's specialized to lipids. Okay, so let's follow some of these possible conversion routes. Okay, so starch. Well, you can, for instance, you can saccharify and ferment. Okay, so when you do this, you get sugars. If you put a banana in the microwave oven, what you get? You get a sweeter banana because the starch content of the banana was transformed to sucrose. Okay, so that's what happens. You know that you have some kinds of pre-treatments here. They are based on microwave. So you get starch, you get sugars by sacharifying. So and from sugars, you can ferment. Then you get ethanol. Then you dehydrate and have some, in order to remove water, as I mentioned. And the point here is that in order to transform, to qualify, you have to satisfy this standard here. Okay, so if you're working in this path here, I recommend you go to the internet and download this standard and see the requirements that you're going to have to attend, to satisfy. Okay, another example is from fibers. I think most of us are working with this stuff here. So what we have to do, we have to first we pre-treat. This is not actually a conversion route, but it's a necessary path. Okay, you can, from this material, you can, for instance, as I mentioned in one of the classes, I forgot which one, you can gasify this material in order to produce syngas, okay, CO and other compounds that you can, for instance, you can use the syngas in order to produce a kind of a kerosene for aeronautical applications. If you are in this route, you are going to have to satisfy this standard here. Okay. Another possibility, we're not talking about thermochemical mostly here, but another possibility is to pre-treat and then hydrolyze, okay, and then ferment. Then you get alcohols, okay, and so that's the norm that you have to have. Okay, so this graph here is very interesting because it shows it's complex at the first sight, but you have all possible conversion. You have a lot of important information in this graph, and I'm emphasizing these standards here because they are very tight. They define, going back one slide, they define this kind of thing. What is the heating value, and a lot of other steps that I'm going to show. Okay, the viscosity that you have to have. Okay, if you don't comply with this specification, you're not going to be able to certify as your product as an aviation fuel. You're not going to be able to sell your product to aviation companies. Okay, and when you satisfy, so suppose let us assume that you somehow you arrive here in this point here. Okay, so you have an aviation fuel that is already satisfying, complying with, sorry, I'm looking for my pointer. Let us assume that you already have a fuel from algae, for instance, or from sugarcane bagasse, for instance, but somehow you manage to pass to comply with all the requirements of this standard here, okay? My point is that's not the end of the story, okay? You have to certify as an aviation fuel, and for that you have to pass a series of tests that are also defined in these standards. So the first, you have mostly 4 families of tests, okay? The first ones are specification properties. They are, for instance, you're going to measure the viscosity at different temperatures to see if you satisfy, okay, if you comply with the standard, okay. So those are lab tests, very small scale tests, okay. A second family of tests is what we call fit for purpose properties in terms of corrosion potential, for instance. Your fuel, is it compatible with this list of materials that that it is going to be in contact with during its use in aviation fuels? Okay, so if it is, okay, you pass the test. If not, you don't pass the test. You got to go back and change probably your production process. So fit for purpose is material compatibility and other types of similar tests, okay? Then another family of tests is component suitability, okay? So you do this in test rigs. Let me cancel, someone is trying to call us here, okay? So for instance, does your aviation fuel works well with this kind of fuel pump here, okay? Okay, if it does, fantastic. If not, you have to go back and maybe change something here, okay? So you have components, you don't have to test it in an actual airplane. And finally, the engine endurance test, because these fuels will fuel this type of engines, okay, mostly turbofans, and the engines themselves must endure several types of situations, let's say like this. These situations may be, for instance, water ingestion. Okay, I'm going to show you some videos on that, but I want to explain first. Why does a jet engine must still work even if you have a lot of water, liquid water entering the engine here? Well, because it's going to fly in the rain, so it must resist to amounts of considerable amounts of water. Okay, so that's what we call endurance test. I'm going to show you some videos on that. Okay, this first one is water. Okay, so you have a series of sprinklers here. Okay, and it's going to inject water, and you see that the engine is not going to stop. Okay, before starting the movie, the video, you see that I want to emphasize one fact here. This is very expensive to be done. You're going to see how these tests are sophisticated, and so it's natural that they cost a lot. So it's very, in addition to be very difficult to qualify as an aviation fuel, it's also very expensive. Okay, so the engine is running, it's going to start injecting water. You see, it's a very huge amount of water, and the engine's still running. So it's very hard to an aviation engine to stop due to water ingestion. You see, it's very big amounts of water, and the engines go okay, no problem. Okay. In a important point, this is a turbofan. That means that I'm going to stop the movie. Let me go a little bit further. No. Yeah, here. You see, it's a turbofan. So this external part here is just a bypass. Okay, so you don't have you only have air at this external area here. This internal area is well, it passes through the combustion chamber, turbines, and compressor. Okay, so and I don't know if you observed, but you see that the injection of water is done in the center part here of the engine. So most part of the water is actually passing through the engine, through the compressor, through the combustion chamber, and through the turbine. So this is a very specific tests. Another test. Let's see. This is the guy who posted this video. And yeah, this is bird ingestion tests. You see, one kind of test that you do also with the airplane's fuselage, okay, is what happens when a bird hits the plane, hits the wing of the plane, but also the engine. So one specified test is bird ingestion test. So you see that these birds are being thrown at the airplane. Okay, you see it must stand to a certain point, obviously. Okay, if you throw a cow on the end, it's gonna explode. Actually, you see. So that's the kind of test that the engine must endure with your aviation fuel. You have to prove that with your specific aviation fuel, the engine is not going to have problems. Okay, you have to perform this test, and my point is that they are very expensive. Okay, you see. Uh, yeah, another one, a very interesting one, is, well, this test, in this particular video, the engine is going to fail, okay, because the object, the bird that was ingested, is too big. And even stopping, even exploding, it must not, I mean, it must stop in terms of mechanical parts. Its mechanical parts will stop functioning, it's going to stop, but the engine must not cut fire. Okay, that's something that you have to prove that your biofuel will stand. Okay, so just a few moments, the engine is going to explode. Okay, let's see. And you're going to see that it's going to vibrate a lot. Yeah, it exploded. So it's stopping now. The speed is reducing. It starts to vibrate. This is a kind of resonance. And the engine is okay. You have some fire here, but it's not in the engine. Okay. So you have to perform a lot of tests like this. And that's the point. They are very expensive. So to develop an aviation fuel, you have to pass through all of these situations here. Okay. So that's one important point. Okay. Um, okay. So I think yeah.
And Professor, is there any possibility of blending by biokerosene with kerosene from petroleum?
Yeah. Yeah. From a technical point of view, yes, you can blend. The engine's going to work, but the same. Anyhow, you have to pass all those tests. Okay, you have to pass through all these tests. You have to prove that your blended fuel is able to comply with all the requirements of these standards. Okay, so blending is not does not avoid passing these tests. Okay, you can do in thermal power plants, for instance. There's a lot of blending in terms of coal and biomass, for instance. But well, the application is much more robust than an airplane, so you don't have these very tight specifications. Okay, I don't know if you asked in terms of avoiding having to pass through all these tests. I'm not a specialist in this area, obviously, but it's sure that you even though you have a blended fuel, you have to comply with these standards here. Okay.
Okay, my
Okay.
question is, I have just already used blending in, I mean, in aeroplane, is there anything like that? Or it's not yet used like automobiles? I mean, you have benzene up to 20%.
Yeah, well, actually, I don't know because, as I said, I'm not a specialist in this field. Okay, but it's very reasonable that if you blend these fuels, you, you're not going to have problems in terms of the engine itself. Okay, because you're blending. I don't know if I made myself clear. You're blending very similar fuels actually, because they already satisfy these specifications, for instance. Okay, so you're mixing very similar fuels. It's not like blending ethanol with gasoline as we do here in Brazil, okay, for the flex fuel cars. Okay, so they are already very similar, but you have to comply with these specifications anyhow. So you have to pass through all these tests here. Okay.
Okay.
Okay, so let's move on. And I wanted to, when you see the small tree here, is that I'm making a detour or focusing on a subject. So I'm going to talk. Well, we were at an end point here. We were talking about aviation fuel. Now I'm going a few steps back, and I'm going to talk again about the whole transportation sector, okay, or as I prefer to say, the energy conversion chain in the transportation sector, okay. Another way to refer to this is what they call the well-to-wheel analysis. Okay, so the idea is to analyze from the sources, the well, okay, to the final application. Uh, if you're talking about a car, obviously, it's when the wheel uh, receives the force from the road that will drive the car, for instance. So the well-to-wheel analysis. So we were at one of these endpoints. We're going back a few steps in order to take a detour and talk about hybrid cars actually. Okay, so first let's talk about this conversion chain. Okay, this conversion chain, well, you start from the sources. I just put a small oil well here just to exemplify, but this source can be sugarcane, for instance. Okay, so you have primary sources. Okay, so you have feedstock here. These feedstock must be converted to what we call energy carriers. Okay, so you have different types of efficiencies concerned here. Okay, so in order to convert some primary source to some energy carriers for instance, in terms of electricity. So in order to convert biomass, bagasse, for instance, or straw to electricity, in order to convert bagasse to electricity, you have to have industrial efficiency. So you're talking about industrial processes. This is the same if your energy carrier or energy vector is some kind of fuel. Sorry for the Portuguese here, okay? If you're converting the source to electricity, you have to have industrial efficiency, or actually this becomes second law thermodynamic efficiency, okay, exergetic efficiency. If you're converting if you're converting this source to a liquid fuel, okay, you have what you want to have a high energy content. So you also have to have industrial efficiency. Okay, you're not burning anything as you're doing here in electricity generation, but you're transforming things. So you have, but still it is industrial efficiency in terms of processes. Okay, let's follow this path here, because electricity, you can convert a primary source, coal or biomass, you can convert to electricity, but you can also generate electricity from renewable sources, as wind or photovoltaics or waves and so on. Okay, so you have an alternative input here when you're talking about electricity. When we follow this conversion path here, okay, once you have your liquid fuel or fuel, simply fuel, okay, you want to transform that to mechanical exergy. Actually, this means a torque times a rotation of some axis, for instance. Okay, so a force times a velocity. This is a mechanical power, which we can refer to mechanical exergy. Okay, because well, you're going to use this mechanical power, okay, to transform, to move your vehicle. Okay, so you want to transform this mechanical power, torque times rotation, you want to transform this to kinetic energy. Okay, so here you have force times speed as the jet airplane. Okay, the gases are being exhausted backwards here. Okay, the reaction to the acceleration of these gases is the propulsive force here in black. Okay, so you want this force times the speed, you have this power, the propulsive power. Okay, so here transformation of mechanical exergy to kinetic exergy, you have to have an important aspect, which is propulsive efficiency. I want to talk about this. That is why I'm explaining all the conversion chain. Okay, I want to talk about propulsive efficiency. And propulsion, well, it's specific to the application. It's something different when you're talking about airplanes. It's different when you're talking about trucks and cars and trains. And another important, let's say, bifurcation of that multi-branched tree is what we call self-propelled vehicles. I'm talking about self-propelled vehicles. I'm not talking about trains or electric trains, because this type of applications, you don't have to carry the fuel reservoir with you. Okay, the energy comes from these wires here, and the train simply gets the energy from the wire and converts it to mechanical power and then kinetic energy. So the problem that I want to talk about is self-propelled. And for these vehicles, you have, in addition to have propulsive efficiency, you must have an efficient energy storage system. Okay, so it's another point that I want to elaborate here. Okay, and I'm going to do this starting with a question. Let's see, a clever question. How does batteries, okay, let me go back one slide. You see that you have mainly two kinds of energy carriers for the transportation sector. You have electricity, which is very good in terms of propulsion efficiency. Okay, electric motors are very efficient in terms of transforming its injected exergy to kinetic exergy. They are very efficient. Okay, but they are poor in terms of storage. I'm going to show you that. Okay, and liquid fuels are not that poor, but let's say they are poor in terms of propulsive efficiency, but they are very good energy storage system. Okay, when we say it like this, it's kind of subjective. So I want to give you a very objective, actually, a very objective idea of this comparison. Okay, so let's start with this clever question. How does batteries compare with liquid fuels in terms of energy storage? Okay, and when I think about batteries and liquid fuels in the transportation sector, I'm thinking about electric cars compared with internal combustion engine cars. Okay, so that's the point. And let's try to build the equivalent of an operation envelope as we did for the whole transportation sector. Okay, only that in this operation envelope, we want two things. We want to optimize two variables or two performance parameters. Okay, we want this energy. I'm going back one slide again. We want this energy storage system to be the smallest as possible, okay, and the lightest as possible. We want it very, very tiny and very, very light, because, well, if it's tiny, it's not going to need a lot of space in my vehicle, okay, and if it's light, it's not going we're not going to need energy to accelerate and decelerate this mass, okay, which contains or fuel, okay. So we can do this with this graph. We can plot the several technologies of energy storage in terms of its volumetric density, okay. So the more volumetric dense a system is, the smaller it can be built, okay, and also kind of a mass or massic density, okay. The more massive this system is, the lighter it can be in order to store a given amount of energy for our application. So what we do, the same that we did for the whole transportation sector, we go to the very multitude of energy storage system and start to plot these points here. We get this result for batteries, for electric batteries, okay? Those are different types of batteries. I'm looking for the lithium batteries. Lithium, okay, so lithium batteries are here, okay, you see. Lithium batteries, and this is the kind of number that you have in terms of its massic density, in terms of let me get my pointer here, in terms of watts hour per kilogram of battery, okay. So you have typically 200 watts hour per kilogram. You can do it by your own. You get a battery from your remote control, for instance, okay. You see the amount of milliwatts hour that it stores, okay. I don't know if this one has, probably not, because it's not rechargeable, okay. Yeah, it's not rechargeable. The rechargeable batteries, they have this information, okay, the amount of energy that it can store, okay, and if you weight this battery, you can produce this number, okay. Also, the volume. So for the same battery, you can measure the volume of this battery and produce this number. So 200 for the lithium-ion batteries, the typical numbers are 200 watts hour per kilogram and 500 watts hour per liter, okay? That's the typical application for batteries. Yeah, how does these results compare with liquid fuels? So when we start plotting liquid fuels in this graph, you get this picture here. Our batteries are here and liquid fuels are here. Okay, so liquid fuels are 100 times, roughly speaking, better in terms of how light they can be, of mass density, okay, and they are roughly 10 times better in terms of the size or volume efficiency, we could say it like this, okay. So actually, there is still a long way to go. If you want batteries to displace liquid fuels as energy storage systems, you have a long way to go. Still have a long way to go in order to have a comparable performance, okay, in terms of liquid fuels. So you see that the main problem associated with electric cars is actually related to energy storage, okay, because batteries are very heavy and big. That's the problem, actually. So that's the problem that you have to have. that you have to solve in order to use electricity as your driving force. Well, so this is, let's say, one point for liquid fuels, but you're going to see that the problem is not the liquid fuel, is how you convert this energy carrier, or the energy contained in these liquid substances. How do you convert this to kinetic energy in your engine? So that's where electric motors are better than internal combustion engines. I'm going to show you this. Okay. So this is why hybrid cars is an interesting solution, because you combine the best of both technologies. Okay, you combine the best storage technology, which is liquid fuels, not even gas fuels. Okay, so you combine the best energy storage technology to the best driving technology. By driving, I mean, I'm going back a few slides, sorry for this. By driving technology, I mean propulsive efficiency, converting the energy source to kinetic energy. Electric motors are fantastic for this conversion, okay? A lot better than internal combustion engines in low-speed applications, okay? So that is why hybrid cars are a very interesting option. And I'm going to elaborate actually a lot on this. At the end of this class, I forgot to say at the beginning of the class, we're going to make a simulation, develop a simulation in order to compare three types of car: an electric car, a gasoline car, and a hybrid car. Okay, we're going to compare three cars. We're going to simulate. Actually an acceleration test. We're going to compare, and you're going to see the results. Okay. Well, let's take a look at other types of energy storage systems in terms of, for instance, you can see here natural gas. So it's very, very, I would say it's very light, okay? Okay, but it's very, its volume is very poor. Okay, that's what I was saying about. Let me erase this because it's going to pollute a lot here. So natural gas is not a very, it's a very good fuel in terms of energy content. It's actually, let's identify gasoline, ethanol, kerosene, and diesel here. Okay, so it's a lot better. It's better than gasoline in terms of energy content, but it's terrible in terms of volumetric efficiency. So that's why gases are poor solutions in terms of self-propelled vehicles. You're going to see some talk in the proper literature. I'm sure you're going to see applications related to using hydrogen. Hydrogen has a very high energy content, but there's still a gas, so it's very poor in terms of volume. You see, this is amazing, 700 bar. Can you imagine what would be a gas tank or a tank for a gaseous fuel that stands 700 bars? Okay, it's going to be very, very thick. It's the tank, not the fuel. The fuel, okay, it's okay in terms of its weight, but the tank that stands 700 bar is going to be something incredible. Okay, well, batteries are here, as I mentioned, and you also have these types of metals here, aluminium. That's why I put this picture on the left, because you have these types of powders, okay, which are very, very good in terms of both massic efficiency and volumetric efficiency. And that is why some boosters, like the booster here of the space shuttle, they run with solid fuel. actually. Okay, solid fuel, because you see they are very well. They have a good energy content comparable to gasoline, ethanol, and so on, but they are very efficient in terms of size. So that is why the boosters of these rockets run with solid fuel. Okay, that's an explanation for this. Okay, so let's move further. Let me talk. I'm still talking about propulsive efficiency. I'm showing you right now a comparison with different engines, types of engine for airplanes. I mentioned about turboprop, turbofans, and turbojets. And so this is the propulsive efficiency in terms of its flight speed, given in function of the corresponding flight Mach number. Okay, for those of you that do not remember, the Mach number is the relation, it's the speed of the airplane compared to the speed of the sound. Okay, at that particular temperature and pressure. Okay, so Mach 1 corresponds to the speed of sound. Okay, you see here that for supersonic airplanes, the most efficient engines are turbojets. Okay, so all the energy of your fuel is transformed to kinetic energy of the exhaust gases, and the reaction of that is the propulsive force. Okay, so I have turbojets here, and this is the same type of engine here. So you accelerate the gases backwards, and the reaction to this force is the propulsive force. Okay. For slow speed applications, turboprops. Okay, so engines with a propeller. Okay, you accelerate somehow you have mechanical power here, so it's going to turn the propeller, and it's going to accelerate the air backwards. Okay, and the reaction is the same way as the propulsive force. And let me erase in order to clean a little bit here. Okay, and well, the mixed efficiency here. So the turbofans, which is the figure, the animated GIF on the left. So the turbofans are the most efficient applications for low subsonic flight speeds, okay, which are speeds very typical in the commercial area. Okay, so for for high subsonic speeds, turbofans are the most efficient ones, the most efficient engines for this application. A turbofan, you can see it here. You see this, let me get my pointer. It's kind of a hybrid engine, actually, because you have some amount of propulsion you get from the jet here. You see, this is the intake. Here you have the compressor, the combustion chamber here, and the turbine. The turbine produces power for the compressor and also for the fan outside here. But you still have gases at high speed here. So let's say 50% of this engine is kind of a rocket engine or a turbojet. Okay, but the other 50% actually is like a propeller. So this external part here works as a propeller. As you can see, the air is simply accelerated, but it's not heated due to the fuel here. So it's like a propeller, and the external air is being accelerated, so you still have some propulsive power from this 50%. So turbofans are a combination, a kind of a hybrid engine, a turboprop combined with a turbojet. So that's the analogy that I'm making. Hybrid cars and turbofans, because they combine the best qualities of two different kinds of applications here. And just an observation, these numbers, the bypass ratio, 1, 3, 5, and so on, is the amount of air that bypasses the engine. Okay, so 5 means that you have 5 times more air bypassing the engine than you have air passing through the engine. Okay, so well, that is why most commercial jet planes work with this kind of engine. Okay, turbojets today are only for military applications. Okay, I would say. Okay, so let's move further, and so talk a little bit about vehicles. You see the tree again. We were talking about aviation fuel. Okay, we came back. Oh, go on.
Professor, please, for jet engine, is propulsion efficiency equal to the size of the engine, or does it matter the size of the engine?
No, it does because you have aerodynamic drag associated with it. Okay, but you know, in practical terms, you can build very small engines here. Okay, because anyhow, it's going to accelerate a lot. The speeds here are very high, actually. Okay, you have I don't know if you heard the term. You have engines, what they call, I think, scramjets, ramjets, and so on. I'm not sure of these names because it's a long time I heard them. But these engines, when you look at them, I'm going to make a drawing here. When you look at how they are built, they are simply a kind of a tube, simply a tube. Okay, you don't need a compressor. Okay, you don't need a compressor as you need here. Okay, so you have a tube, you have fuel injection, then you have combustion, and you have gases being accelerated. So they are very simple engines and very small engines. But as you can see here, they are very inefficient at low speed. So when you are at cruise flight mode, at Mach, for instance, Mach greater than 2, for instance, so these kind of engines work very fine. But at low speed, at Mach numbers smaller than 1, they are very inefficient. So you can figure out how inefficient an airplane like this is at takeoff and landing, for instance, because you cannot land at this speed. Okay, you're going to need 100 kilometers. I don't know how to decelerate. Okay, so I don't know if I answered your question, but what I wanted to say that these engines are very simple engines actually, but well, since they are very inefficient at low speed, they are not viable for commercial applications. Okay, and that's why we saw the Concorde and similar airplanes being retired for commercial applications. Okay. Okay, so let me move on, and as I was saying, we were talking about aviation fuel, then we came back, we talked about the whole conversion chain or the whole conversion pathway, and now we're talking about propulsion efficiency, and I wanted to talk a little bit about hybrid vehicles, and that's why I made this analogy, the turbofan, which combines two different driving technologies. Okay, so the hybrid car is more or less like this, not exactly, but I want to elaborate a little bit on this. Okay, so let's see what actually is a hybrid car. Okay, so a hybrid car, actually, the problem is that well, it's more complex than the analogy that I made, the turbofan. Okay, actually, you may have several different what we call topologies or architectures of a hybrid cars, or several kinds of combinations that you can, and each one will bring about a different family or hybrid car. I want to show you this. Okay, so a typical one. This is a concept model from BMW. So you have an internal combustion engine here. Well, those are the actual specifications. A 300 kilowatts internal combustion engine. Okay, and you also have an electric motor, 15 kilowatts. Okay, and I want to show you why the power of the electric motor is much smaller than the power of the internal combustion engine. Why is this? Again, you don't need to have this situation. You can only have, for instance, there are some cars that use only an electric motor, okay? But I'm just giving you an example. But this one is very good because it has all the basic components of a hybrid car, okay? It's going to become more clear in the next few slides, okay? Just to explain the parts here. I think I'm going to zoom here, okay? So we have the internal combustion engine, a very high power internal combustion engine, and a smaller electric motor. It's here, okay? Built in this transmission X here. It's a small power, but a very high torque. I don't know if you are used to these numbers. A typical car, probably the ones that we have ourselves, the torque, the typical torque is something like 30 to 50 Newton meters. Okay, so this one is a very high torque. So it's going to be very good at acceleration. We can already imagine this. So this car, this concept car, actually, okay, well, you can buy it, but it's too expensive for the performance. Okay, so you have two engines or two motors, an engine and an electric motor. Okay, you also have two types of storage. You have two types of energy. So you have batteries and you also have tanks for liquid fuel. Okay, so that's why it's a concept car. It's a very, it combines everything actually. So you have two motors and two energy storage system. You also have another element here, a very important one. It plays a very central role, is what we call the power split. Okay, this is a mechanical device I'm going to show. It's a kind of a gear assemblage, okay, that receives power from the electric motor and from the internal combustion engine and add these powers and sends it to the drive shaft, okay, in order to move the wheels, okay. So this power split, it's another very important element in a hybrid car, okay. Someone is insisting in calling us, okay. Well, so this is a typical hybrid car. Well, you also have traction wheels. Every car has this kind of thing, okay. And okay, so that's the point. Let's see in detail some of these elements. The power split actually is what we call, it's a kind of a gear assemblage, and what we call, I don't know which one of you are familiar with this kind of element, is a planetary gear system. Okay, so you have an external gear here. Okay, you have an internal assemblage and the internal X here. I think it's easier to see here. Okay, so this kind of assemblage you can use for very different applications actually, but you can have, for instance, your electric engine or your electric motor driving this external gear here or internal gear here. Okay, the internal combustion engine may be driving this one, and the shaft may be connected to this gear here. Okay, so the point is it mixes, it combines the power from two different sources. Okay, So one possible configuration, knowing the parts now, two types of motors, the power split element and the energy storage systems, we can combine these elements in several different ways. Let's see some of these configurations. Okay, first, the one called serial configuration, which is a very efficient configuration in terms of, I would say it's a fantastic for urban applications. Okay, so a serial hybrid car is actually um, an internal. It has a fuel reservoir. It runs only with fuel, liquid fuel. Okay, well, it has a small battery, but you're going to see. So the main part of its energy stored for the application comes from the fuel reservoir. Okay, and this fuel feeds an internal combustion engine. Okay, which drives an electricity generator. Okay, and this electricity goes to, well, a small battery actually, and the electricity drives the electric motor, okay, which drives the wheels. So this serial car actually is an electric car in terms of the drive technology, okay, but uses liquid fuel as fuel reservoir, energy reservoir, okay. It's very efficient for some specific reasons here. First, it has the best storage system, which is a liquid fuel, okay, and also it uses a small stationary combustion engine, because this engine here is not going to be used to drive the wheels. It's used only to drive the electricity generator. So you don't need a big engine. You need a small engine, and by stationary, I mean not that's going to stay in place, but it's going to work at a constant rotation speed. Okay, so RPMs here, the RPMs of this internal combustion engine is constant. And so knowing that it's stationary in terms of its rotation speed, it means that you can optimize your internal combustion engine for that particular speed. Okay, so this speed here has nothing to do with the speed of the car. Okay, it's simply nominal speed for which the internal combustion engine is optimized. Okay, I'm going back 2 slides. In this case, or in the case of a typical internal combustion engine car, the internal combustion engine has to work at very different kinds of speeds. When you are at home parking your car, you are at very low speed. When you are traveling on a road, okay, it's asking me to put my cell phone in airplane mode, so I'm gonna comply. Okay, sorry, just a moment here. Okay, airplane mode. So I was saying that for a typical car, the internal combustion engine has to work at very different speeds. So you cannot optimize the engine for a single rotation speed. Okay, and you pay in terms of efficiency. So it can perform at very different speeds, but it's not going to be as efficient as it can be a stationary combustion engine. Okay, so this kind of engine, stationary combustion engines, are actually used in generators. Okay, so you have the most efficient storage system. You also have the most efficient internal combustion engine for that application, which is a stationary combustion engine, and you also have the best drive system, which is an electric motor. I didn't explain why the electric motor is the best drive system. I'm going to show you, I'm going to explain in a few moments. But I can already say something right now. For instance, when you're braking, if you want to reduce speed, you can do two things. You can, well, step on the brakes, okay? It's going to produce drag here, okay? But there's another thing that you can do. You can use the electric motor. You can transform this electric motor into an electricity generator, okay? So instead of the motor driving the wheel, okay, it's the wheel that is driving, not the motor, but the electricity generator. And the electricity generator, the electricity generated during brakings can be stored in this electrochemical battery. So you recover the energy when you reduce, when you want to reduce the speed. Okay, so this is a very important aspect for urban applications. Okay, in average, 13% of all energy spent by a car is during brakings. Okay, and this amount can be recovered with this configuration here. Okay, so what we call the serial configurations is very efficient in terms of energy use and also size, and I would say also price. Okay, but the electric motor is not that good at very high speeds. I'm going to show you this. Okay, let's move on. Another possibility is what we call the parallel configuration. Okay, so a parallel configuration will need a power split, as I was saying. Okay, so you have two cars actually. You have an internal combustion engine car. Okay, it uses a fuel reservoir, an internal combustion engine, and you also have a battery and the electric motor slash generator, because as I mentioned, you can through the generator you can recover the energy when you want to reduce speed. Okay, so in this configuration, the power split combines, okay, the mechanical power coming from the internal combustion engine combines this power to the power coming from the electric motor. Okay, so it adds these two powers and sends it to the wheels in order to move the car. Okay, and also you can see the electric motor can work also as a generator. That's the situation when the mechanical power comes from the wheels and goes to the generator and becomes electricity stored in the battery. Okay, so this is actually the car that I showed you, the BMW car. Okay, in the previous slides, and well, in this situation, you have actually two cars being combined through this power split. Okay, this is a very interesting configuration for performance, because you can extract the best performance, or you can use the internal combustion engine at its best performance situation, and likewise for the electric motor, simply by changing the logics behind the power split. That's exactly what we are going to simulate. Okay, we're going to build a spreadsheet and make the calculation in order to simulate these different technologies. Okay, yeah. So let me try to become a little bit more technical right now, because we want to make the simulations. Okay, I mentioned that the electric motor is not very good at high speed, but it's very, very good at low speed. Let me explain why, and also why the internal combustion engine is poor at low speed. Okay, but it's quite good at high speeds. Okay, let me show. This is related to the power curves of these engines. Okay, these curves are characteristics of both the electric and the internal combustion engine. This is for the electric motor. So you have torque here. Torque is in terms of force times a distance, or a torque times the radius, okay? So you have torque here and the rotation speed of the engine, okay? This is a typical curve of an electric motor, okay? The most remarkable feature here is that at zero rotation, you have a finite torque and actually close to the maximum torque, okay? What does this means in terms of performance? For instance, when you're stopped at the red light, for instance, so the rotation is zero, okay? The rotation is zero. When you want to accelerate, you simply, well, you inject the electricity, it's going to produce a torque that's going to be transformed to a propulsive force. So you start accelerating your car at almost the maximum possible force. Okay, so it's very good at accelerating. Okay, and why is this possible? Because in order to have torque, in order to have force, what do you need to have in the electric motor is the corresponding magnetic field. Okay, and to have this magnetic field, you have to have electric current, okay, through the coils of the electric motor. So no problem. This you don't need to have speed in order to have electricity in the coils of the motor. Okay, so that is why you may have torque at zero rotation speed of the motor, because you simply assure that you have electricity running through the coils. Okay, and that is why its performance, the torque, drops down to near zero at high speed, because you have a problem of the magnetic fields being detached from another. Okay, so its performance tends to drop at higher speeds. Okay, so the electric motor has this characteristic. Its torque is near to the maximum at zero speed, rotation speed. Okay. Now let's analyze the internal combustion engine. Okay, its characteristic curve starts from zero, as you can see. Okay, it reaches a maximum, then it drops. Okay, let's see why it starts from zero here. Why it's zero? Because, well, in order to have torque in the internal combustion engine, you have to have what? You have to have fuel, you have to have explosions in the internal combustion engine. Okay, you have to have fuel and oxidant, air, okay, entering the chamber, then it cuts fire, then it explodes. So in order to have this, the engine must be running, okay? The speed of the car must be running, okay? And just an observation, that is why you need a clutch. For the electric car, you don't need a clutch, okay? But for the internal combustion engine, you need a clutch, okay? So, if the car is not running, its rotation speed is zero. If you have a clutch, okay, you may leave the car stopped and the internal combustion engine may be running, okay? So, so that is why its torque starts at zero, okay? Then it goes to a maximum, and then it drops. It starts dropping after a certain rotation limit. Why? Because the problem here is related to the capacity of fuel and air, mostly air, not fuel, because fuel may be injected by a pump, but air, it's going to, you have pressure drops actually. Air must flow through the filters into the admission manifold, okay? And at high speeds you have pressure drops which will hinder the amount of air that is entering the internal combustion engine, okay? So you start having problems in terms of making the air get into the combustion chamber. So that is why it drops. But it reaches a maximum around this situation, around the given rotation speed. I'm going to use this slide in order to, I'm going back a few slides just to comment on something here. So this, yeah, here. I was saying that this internal combustion engine is stationary in terms of its rotation speed. When we compare this graph here, you see that its maximum power torque in this case, it's not a peaked curve, okay? And that is why I explained that since the car is going to work at very different speeds, okay, you design an engine that produces high torques at a very wide range of rotation speed. That's related to the kind of application. When you have a stationary engine, you can develop an engine like this, something like this. You may have a very higher torque, okay, at that particular rotation speed, okay, and well, its performance will drop drastically if you're not at this speed. But in the serial configuration, the engine is stationary in terms of the rotation speed. So you can use this type of engine, which is a lot more efficient in terms of fuel consumption. Okay. Okay. So the internal combustion engine has this characteristic. Sorry, I'm just erasing something. So the internal combustion engine has this kind of typical characteristics. It's well, it starts at 0. Okay, its torque is near to its maximum at a certain nominal speed. Okay, and well, this fact here explains why we need a clutch, and also the fact that, well, it has a wide range of rotations, but it's not, we're going to see, it's not enough to cover, for instance, from 20 kilometers per hour to 120 kilometers per hour, okay? So the range of rotation is bigger than this, so that is why we're going to need gears, different gears. The electric motor does not need gear and does not need clutch, okay? But the internal combustion engine needs both of these devices. So let's see how a hybrid configuration could work with these two types of motors. Two types of motors, okay? So the power split is going to combine these two torque curves, the electric motor torque curve and the internal combustion engine torque curve. And this combination is going to follow kind of a logic, which is represented here in this graph, okay, for the parallel configuration. For instance, below 4,000 RPMs, okay, you use 100% the internal combustion engine, okay? Above, I don't know, 5,000 RPM, you use, that's the exact opposite I'm talking about, okay? So the red curve here, the red dotted curve here represents the electric motor, okay? And it's going to be multiplied by this red solid curve here, okay? The blue dotted curve represents the internal combustion engine curve, and it's going to be multiplied by this solid blue curve here, and then we add both torques, okay? This can be done through this kind of gears. Okay, so let me get my pen, at let's say 2,000 RPMs, we have 100% electric motor. Okay, get another color here. At let's say 6,000 RPM, we have 100% the internal combustion engine. Okay, and at 4,000 RPM, we have 50-50. Let's say that we have, let me get another color here, green, for instance. At 4,000 RPM, we have 50% coming from the electric motor and 50% coming from the internal combustion engine. Okay, so that is exactly what the power split does. Okay, just another last example. At let's say 4,500 RPMs, we get 75, 25%. Okay, that's the idea. And okay, so we have different kinds of logics to make this combination. But we're going to use this one, this very simple and obvious one. When we do the calculations, and I'm going to show you that these curves here are actual curves from actual engines, okay, in electric motor. And when you combine these curves, you get this curve here. And the point is that you have the best qualities of both. You see that you have high torque at low speeds, okay, and you have a very high torque, okay, at very high speeds, okay, because let me do not disturb. Let me try this option here, okay. So the resulting curve, the red curve here, combines the best qualities of both engines. Okay, so we expect to have a very good acceleration if we're going to test this car, and it should have a very good performance at high speed because the torque here is still high at high speeds, and this is because it's coming from the most of the torque is coming from the internal combustion engine. Okay, so we're going to simulate this, okay, in order to try to answer this question. Which is the best power transmission system? Okay, let's try to answer this question. And again, we see the multi-branched tree. So again, I'm coming back a few steps in order to because I already described the hybrid cars, but now I want to compare different technologies for different kinds of applications. Okay, so let's see. When you say better, we should specify better in terms of what? Okay, we can talk about energy and emission efficiency. Okay, so I would say the electric car is the best one, provided that the electricity is not being generated from a fossil source. Okay, so if you use wind or photovoltaic or even, roughly speaking, nuclear power, it's not exactly renewable, but the amounts are very, very significant, so to be compared to a renewable source. So if the electricity is not being produced from fossil resources, okay, so the electric car is the most efficient one. Okay, its electric motor is optimized for drive and also braking, as I mentioned. Okay, in this configuration, electrochemical storage is inefficient and problematical. Also because for these batteries you need special types of metals and ions and so on, and you may end up with a similar problem, okay, in terms of where are you going to get lithium for all batteries of all cars in the world, okay, so you may have a different kind of problem. If you're talking about still talking about emissions and energy efficiency, the hybrid cars are, I would say, a better choice because it avoids the problem of having huge batteries. Okay, this serial configuration has a small battery. Okay, so it is actually liquid fuel. It uses actually liquid fuel. Okay, so it combines the best storage technology, provided the fuel is not produced from a fossil source. Sorry, a fossil source. Okay, so if you produce from bioethanol, for instance, you don't have problems with emissions. Okay, and since it is a serial configuration, this battery may be very small, so you don't need significant amounts of weight and volume of battery for this application. Okay, so in this configuration, we still have the electric motor, which is optimized for slow speed and particularly for intermittent application, braking. Okay, energy storage is the best is the best technology. Okay, and as I mentioned, fuel produced from renewable sources, you avoid problems related to emissions of greenhouse gases. Okay, this is, I would say, a very interesting application for urban scenarios. Okay, because, well, as I mentioned, the electric motor tends to lose performance at high speeds. But you're not supposed to be at high speeds in the cities, so it's a very good solution for cities. I don't know if you know, I know very well this in Paris. You have this Autolibs. It's like renting bicycles. Okay, you put your credit card here, and you get the electric car. You can use it for some hours. Then you park the car again. You plug, and it charges the battery. So it's a very interesting solution for urban areas. You have the best. You don't have the problem associated with the electric motor because you're never at high speed. Okay. Yeah.
Teacher, how affordable is this technology?
Sorry, I didn't hear you.
How affordable is this kind of technology?
So I'm not understanding you. Can you repeat the question?
The question is how affordable is this
Ah, how affordable? Okay, yeah. No, it's actually comparatively cheap in terms of the alternatives that you have in this kind of situation. Okay, in the central region of Paris, if you get a cab, for instance, a taxi, you're going to spend a lot more than if you rent this kind of car. Okay, and
teacher?
yeah,
I saw this same system in New York City,
yeah.
but that gas station about to electricity is free because it uses the solar power, you know.
Yeah, yeah. There's yeah, the very interesting example. Thanks for bringing it up. My point is that the cost, how affordable. Your question was how affordable. Well, depends on your alternatives. Okay. In Paris, I prefer to walk actually because I'm never working. Now I don't work anymore in Paris. Okay, I've been there several times for work reasons, but now I prefer to walk. But if I had to work, well, at the time we didn't have this kind of solution. But if you have to work and if you have to go to point A to B in Paris, I would say this is a very good solution. By car, I mean, because if you get a taxi, it's going to be a lot more expensive. Okay, and well, you also have advantages, not for yourself directly, in terms of how affordability, for instance, but you reduce the number of cars in the city, so you have less traffic jams. Okay, you reduce emissions, so you have less pollution. Okay, you have several advantages, which are advantages, but they are indirect. Okay, for yourself. Okay, so I think this is a very good solution for urban applications. The electric car for urban applications.
Teacher,
Yeah.
could you buy this car or you rent this
No,
car?
you rent. You rent. This is exactly the same as renting a bicycle. We have this in Rio de Janeiro, in Unicamp. Unicamp, I think you have these bicycles inside Unicamp. Okay, I'm not sure. Guys from Unicamp can confirm this.
At the end of the
Yeah. So this is an electric car. It's not a hybrid car. This is pure electric cars. Okay. The problem with electric cars are batteries. So you cannot have high autonomies with this kind of application. Okay. But you're not going to travel 5 or 6 hours inside Paris, okay? You're not going to. You're not able to because it's too much cars. Okay, so it's a very good solution for urban application. Okay?
Yeah, but it is nice because you can rental a car. In New York, it's just the gas station,
Yeah.
but the
Hmm.
electricity,
Yeah.
you can't buy rental a car.
Yeah. Yeah, well, just to add another point, in this kind of scenarios, you have to have several types of solutions in terms of transportation. For individual transportation, you have to have a solution. For mass transportation, you can take the subway, for instance, both in Paris and in New York. It can go anywhere. But I don't know if you're transporting a cake, a birthday cake, you probably you're going to avoid the subway, for instance. You know, that's a legitimate concern. Okay. Okay, let me move on, okay? And now, I was asking which one is better. Now, depending, if you're talking about emissions, well, the parallel configuration is also interesting because, as I mentioned, if you have the primary sources not related to fossil sources, that's okay in terms of emission. Okay, and the parallel configuration is also very efficient in terms of energy use. Okay, well, let's change the focus. Now, I'm not talking in terms of energy efficiency or emission efficiency, but in terms of performance. Now, that's another bifurcation. We came back a few steps and we're going to talk about performance, comparing performance of different driving technologies. Okay, when you talk about performance, it's going to depend on. Yeah, you have several bifurcations here. You can have highway conditions, or I mean high speeds, okay, or urban scenarios in which you have typically low speeds and also a very intermittent usage of your car. Well, you may thinking think related to performance, you may think in terms of maximum speed, acceleration, if you are competing, for instance, yeah, for a competition. Okay, so we can simulate all kinds of scenarios. Let's just for the fun, let's focus on this kind of situation. Okay, we are competing and we want to get the best performance of our car. Okay, so let's see which one is better for competing in terms of maximum speed, acceleration, and so on. Okay, so let's see. The point here is to show you how you can build a simulation, write down some equations to describe these different kinds of cars and how you can simulate a competition between these different technologies. Okay, so let's make an acceleration test with 3 different cars: electric, internal combustion engine, and hybrid. Okay, let's do this. So the idea is to compare these 3 cars: hybrid, electric, and internal combustion. And this competition is actually an acceleration test. So we accelerate from 0 to 100 kilometers per hour. Okay, and we're going to see the maximum, which one performs better in this kind of tests. Okay. Well, another important point, a very crucial one, I would say, when you compare things, you must compare comparable things, okay, or equivalent things. So that's an important question. That brings about an important question. How is a electric motor comparable or equivalent to an internal combustion engine motor or to a hybrid motor? Okay, how can you have equivalent motors, as I'm stating here? Okay, so that's a crucial point of the class, and I'm going to show you how. Okay, so let's see some equations first. So our car is here. Okay, I have to define some parameters here and variables in order to make the simulation. This is an actual simulation. I'm going to take this car's specification is a Mitsubishi, okay, ASX. It's the wheel radius is 33 centimeters, okay. So this is the torque applied here, okay, to the wheel. The rotation is omega, and well, the wheel pushes the soil back, and the reaction to this force is the propulsive force here, okay, forward force, okay. So the relation between the speed of the car, the speed of the mass center of the car, and the rotation is given by this relation, V equals omega times R, okay, and well, depending on the gear that you are at, okay, the transmission relation, so you may have different transmission relations. I'm going to show a better sketch of this in a few moments, okay. So this is one first equation, working equation, okay, and as I mentioned, we're going to use actual data for this simulation so that our simulation is the most realistic as possible. So you can go to the supplier's website and download this specification. So I took this one. So that's this is the model that we're going to simulate. That's the transmission relation, first gear, second gear, and so on. Okay, and that's the internal combustion engine power and torque curve. Okay, we're going to. This is the starting point, an actual internal combustion car. Okay, that's the maximum power and maximum torque. Okay, so we have all this data, and now we're going to virtually build an equivalent electric car and an equivalent hybrid car, and compare those three cars. Okay, so when we have that's the curve, okay, the actual curve of the internal combustion engine motor, and that's the transmission relation. So well, let's just follow here. The engine is turning at omega, that's the engine rotation, or the engine's shaft rotation, okay. You have gears here, so you have a multiplication or demultiplication, okay. So you have the cardan's rotation, which becomes rotation to the wheel, okay. So you have several gear relations actually here, okay, and this is summarized in this parameter here, A. Okay, so A actually, which is the relation of the engine's rotation to the wheel rotation, okay, and it's defined as the differential relation, which is here, okay. You have a relation because you have gears, okay, so you have a relation here, which is fixed. Actually, you don't change this, but you can change gears, okay. So in first gear, you have this relation. That's the relation with between omega and the speed of the vehicle, okay. Here, first gear, second gear, and so on. Okay. So the point is, our engine is always between 0 and 7,000 RPM. Okay, the engine, that's the whole interval of rotation speeds of the engine, between 0 and 700. Okay, the speed of the vehicle will depend on the gear. Okay, so if you are first gear at 7,000 RPM, okay, you are at 50 kilometers an hour. And those are actual data from that particular car. Okay, at second gear, you are at 100 kilometers an hour, and so on. Okay, so that's the geometric transmission relation. Okay. Okay. So let's move on. Let's look at the torque curve now. Okay. When you now the graph, it's not well, the engine, as I said, going back one slide, is always between 0 and 7,000. Okay, 0 and 7,000. Okay. The torque curve will depend on the gear. Okay, so first gear, that's the torque curve. Okay, you see that beyond a certain rotation, it's better to change gear. Okay, let me zoom on this graph because it's interesting. So let's simulate. I know all of you have experience with cars. Okay, so when you start accelerating, you put the first gear. Okay, and beyond a certain speed, you feel that it's better to change gear to the second gear. Why is that? Because you feel that the torque is coming down, and if you change gear, you're going to follow this orange curve here. Okay, so you still have torque. When you change gear, the rotation of the engine slows or diminishes, then you can have a better, can work under a better rotation. Okay, so that's what happens when you change gear. When you change gear at the proper moment, so you start at first gear, okay, change to the second gear, third, fourth, and fifth. Okay, so the resulting curve, if you change gears at the proper moment, that's an automatic car does exactly this. Okay, so the resulting torque in terms of the speed of the car, not the rotation of the engine. Okay, the speed of the car is this red curve here. Okay, so that's the torque curve, and that's why. The end speed will depend also on aerodynamic drag and so on, but this is a simple geometric relation. Okay, it's going to drop because you don't have gears anymore to change. Okay, so that's it. Yeah. Okay, so let's first try to characterize the torque curve of the internal combustion engine. It's written electric, but yeah, we want to build an electric motor that has an equivalent torque curve. But we know that an electric motor will, for instance, start not at 0, but at near the maximum torque. Okay, so our equivalence criterion will be having the same maximum torque, okay, the same limit torque here, and the same average torque, or the same area under this curve here. Okay, so the electric engine torque curve will be this yellow one, and the characteristic of this yellow curve is that it has the same maximum torque, the same limit torque as 7,000 RPM, and the area below these curves are the same. The average torque is the same. Okay, so that's our criterion. Well, is it possible to find an electric motor like this? Not exactly like this, but you find, yes, you can find similar motors. The problem is that you're not going to find equivalent cars. So the idea is that, well, this is the most similar electric motor. So I buy this motor and I buy a car, take out the internal combustion engine and install this motor inside the car. Okay, so now we have all mechanical and geometric characteristics the same because it's the same car, and we have an equivalent motor in order to compare both technologies. Okay, so just to summarize, we have an electric motor with an equivalent torque curve. Since the torque curve cannot be the same, our equivalence criterion will be the same maximum torque, same average torque, and same limit torque at 7,000 RPM. Okay, so let's move on. The hybrid car is going to be built with these two motors here, okay, following this logic, combination logics. Okay, so below 2,500, you have 100% electric, okay. Above 5,500, 100% internal combustion, and between these two speeds, you have a linear combination of those, of both. Okay, so that's our hybrid car. Okay, that's our hybrid car. Those are the parameters. I'm just giving you, if you want to repeat the simulation, that's the torque curve of the internal combustion engine. MCI stands for motor de combustão interna in Portuguese, internal combustion engine. Okay, those are the characteristics from the supplier's manual. Okay, and that's the equivalent curve for the electric motor. Okay, so this parameter A here, small a, was calculated as 1.141 in order to satisfy this criterion here, the same max, the same average, and the same limit torque. Okay, so that's how we assure that we have equivalent motors to compare. Okay, because it wouldn't be fair to compare different things. So the electric car has an advantage. If you install electric motor in a car with gears, you're not going to need to use, because you see, well, if you use gears, you see that you have in first gear you have this curve, so you don't need, you can use the fifth gear without any problem. It's going to be able to start moving. You don't need a very reduced gear because it has maximum power at low speed. Okay, so you may have a fixed transmission relation for the electric engine, okay, and also for the hybrid car. So the resulting torque curves for the three cars are this one is for the internal combustion engine. You see, you still need clutch because the torque curve still starts at 0. Okay, so you need a clutch. This is for the pure electric car, and this is for the hybrid car. And just an observation, the configuration is the parallel one. Okay, so we combine both torques from the electric motor and from the internal combustion engine motor. Okay, so some kinematic equations now. Okay, differential equations for our movement. We have the torque curve now. Okay, so the torque applied to the wheel, we know they are coming from these curves here, which are represented through these equations here. Okay, and this one for combining both torques through the power split. Okay, so this is the torque curve. This is the transmission relation, which will change for the internal combustion engine car. Okay, so a torque times the radius is the force here, okay, applied to the car, and this is equal to what? Second law of Newton. Okay, mass times acceleration, dv dt, plus the drag force of the car, okay, resulting from the aerodynamic drag. Okay, and we model this drag force through this Cx coefficient, which is also given. I don't know if we go back. If we go back to this data sheet, somewhere here you can find the Cx. I don't know if it's here. Yeah, I'm not recognizing, but anyway, that is also given by the supplier. Okay, 0.33. Okay, so S is what we call wet area, or the frontal area of the car, or projected area of the car. Rho is the density of the air, okay, and V squared divided by 2 is proportional to the kinetic energy. So this equation is a very simple. That's F, okay. Let me write this equation down. So here we have F, which is this force here, F, equals to drag force, Fd, and we could say an inertia force, okay? The force necessary to accelerate at this rate here, okay? So this is actually a very simple equation, and we have everything that we need to solve it, okay? So first we can do a very simple calculation. What is the maximum speed attained by these cars? For this, since the maximum speed, you don't have acceleration anymore, okay? The maximum speed occurs when the driving force equals the drag force, okay? So you don't have acceleration anymore, so this becomes 0. And this, you can see this, you can solve this directly from the equation, but you can solve this also looking at the graph. So this is the force curve, okay? You simply multiply by A divided by R, okay? And when this blue curve crosses this orange curve, which is only this component, okay? This orange curve is this component, and V is here, okay? So when these two curves crosses, you get the maximum speed. So the electric car, the internal combustion engine car, the maximum speed is 207 kilometers per hour. The electric motor, 184. You see it's slower because the torque drops drastically, okay? Also, that's for the hybrid car, 208, okay? So that's the maximum speed. What I want to show now is to calculate the acceleration from 0 to 100. The acceleration time required, or the time required to accelerate from 0 to 100. Okay, so we have to solve this differential equation. We can do this through finite differences. So if we define a partition of time and velocity, okay, you see the point here is that this speed here, this derivative here is approximated by delta V, delta T. Okay, so you are able to calculate the next speed, or the speed at time k plus 1, okay, by isolating this term here, and you get this equation. So you start by setting V0, which is going to be 0 because starting from 0, okay, then you calculate V1 and so on, okay. We can do this in very simple manner. Before showing you the results, before discussing the results, I did this in a spreadsheet, as you can see here. Let me just explain the spreadsheet, and then I will post a link on Facebook so you are able to download this spreadsheet if you want to analyze or modify or whatever you want, okay? So you'll have some parameters here: the wheel radius, the gears, okay, the differential relation, mass of the car, frontal area, Cx, density, and dt, okay? So that's the equation that is being simulated. Okay, so times is running here, okay? So this is the speed of the internal combustion engine, electric car, and hybrid car is being simulated here. Okay, an important observation: how can we simulate the effect of the clutch? If I start all three cars at 0, if I put 0 here, for instance, you see that the internal combustion engine is going to remain at 0. Okay, because if torque is 0, force is 0, acceleration is 0, and the car remains stopped, remains in the same position. And that's why we need a clutch. What is a clutch? The engine is still running, is still turning, the axe, okay? But the wheel is fixed, is stopped, okay? When you clutch, some of the kinetic energy of the engine passes through the clutch and goes to the wheel and starts moving the car. This very small starting speed, okay, this is kind of a bump, okay, start moving the car, and then the car can start to accelerate. So the idea to simulate the clutch is to put a very small speed here, okay, and you see that the movement is able to start. Okay, you already are able to see that the acceleration, the initial acceleration of the internal combustion engine car is very smaller when compared to the electric and hybrid car. Okay, you can already see this. Okay, well, I'm not the idea. We don't have time actually, but I'm going to post the link so you can download this spreadsheet and you can. It's very simple. The only equation that is programmed here is this one for the simulation, and you also have where you have the torque curve programmed in Visual Basic. So if you type Alt F11, you see these functions. The function that defines the power split logics. Okay, you have everything you need for the simulation here. Okay. Okay, so let's go back to the presentation and see the results. So just to remind, I'm simulating this curve for 3 cars, and that's the result that we get. So this is the acceleration time, this is time, okay, and this is speed. Okay, let me go back to the Excel spreadsheet just to show you that those graphs are actually here. Okay, those graphs, for instance, this one for the combustion engine is this column here. Okay, so the results are in this spreadsheet. So what we get, we see, as we expected, the electric car, which is the red one. Sorry, I forgot which one. The electric car is the red one. Is it? Yeah, I have a color code. So the yellow one is the electric, okay? The orange one is the internal combustion engine car, and the red one is the hybrid car, okay? So let's see. Yeah, the yellow one is the electric. So you see that the electric and hybrid cars, they accelerate very fast in the beginning with the test because the corresponding torque curve has a maximum torque at low speed. Okay. The other result here is that the internal combustion engine car takes a long time to start accelerating, then it accelerates properly, I would say. Okay, because well, you have that effect of starting at a low clutch. Okay. So when we want to calculate the acceleration time to achieve 100 kilometers per hour, you simply read the time when you have 100 kilometers per hour. So the hybrid car gets there first, okay? Let me zoom here. I think it's better if I zoom here, okay? So the hybrid car gets there first in 6.5 seconds. Then 18.1 seconds the electric car, and things are changed here. Okay, so the electric car gets there in 10 seconds and the combustion engine in 18.1 seconds. Okay. Okay, and this is the effect of our clutch. If we change, I did this, I'm going to show you. If we are more, let's say, violent when starting the movement, you are able to to reduce significantly this time. Okay. Well, let's see the other result. The other result is in terms of which one arrives first. We know that the hybrid car arrives first at 100 kilometers. But if we were racing, if we fix the time, not the speed, let's say after 60 seconds, which one is in front, which one is in last position? Okay, sorry. So the results are similar. Okay, after 60 seconds, the hybrid car is in front of the internal combustion engine, which is in front of the electric car. Okay, why is this? Because, as I mentioned, for two reasons actually. Because the hybrid car has a slightly bigger maximum speed. I'm going back a few slides to show you the maximum speed. Okay, so it has a greater maximum speed. Okay, but also because the hybrid car accelerates as fast as the electric car, which is the yellow curve here, but the hybrid car does not lose performance. Okay, because at higher speeds, the electric car starts to lose performance because its torque curves starts to drop down. I'm going back one slide at higher speeds, the corresponding torque curves starts to drop, okay, and this effect is not as significant for the hybrid car. Okay, so that is why the hybrid car finishes in the first place here after 60 seconds. Then the internal combustion engine car, as you can see here, or even here, okay, it starts. It has a hard time starting accelerating or starting the acceleration, but when it starts, it recovers. Okay, it passes the electric car after, well, not at 100 kilometers per hour, but after this, okay, and then it reaches almost the same maximum speed as of the maximum speed of the hybrid car. So we can see this effect here. Let me zoom. Okay, let me zoom this. Okay. So the internal combustion engine has a hard time starting to accelerate, but since its performance becomes better at higher speeds, and the electric car starts to worsen. Okay, so there's a moment after 1.5 kilometers when the internal combustion engine passes the electric car, and then after 60 seconds it's in front of the electric car. These numbers here are the difference. If you look at the spreadsheet, okay, so that's the internal combustion engine is roughly 200 meters behind the hybrid car, okay, and the electric car is roughly 300 meters behind the hybrid car. Okay. Okay. So this this simulation, in these simulations we disregarded several facts. So you see that you're never going to get these speeds with these cars. Okay, because as I said, we disregarded several effects as, for instance, transmission efficiency. We consider only drag in terms of some effect that is stealing energy from the process, okay? But you have other sources of inefficiencies which we disregarded. But, well, we can take this into account in a more elaborate simulation. Why this is important? Because, well, you see, from these simulations, the electric car seems to be the worst one. But remember, I mentioned that the electric car is very simple. It does not need gear. Okay, so you don't have power loss due to gear inefficiencies. So when we take this into account, probably the electric car is going to do a lot better. I don't know if it's going to be better than the hybrid car or better than the internal combustion engine car. Okay, but the point is we can always simulate. We can always take these effects into account. Okay. Yeah. Okay. So just some points to conclude, or some observations. The hybrid car has two motors, and hence should be heavier. Yeah, of course, it's not surprising that the hybrid car behaves better, performs better. It has two motors, and we are able to extract the best characteristics of these two motors at different speeds through the logics of the power split. So it's not surprising that it performs better. Okay. The second observation related to a more practical application is that the power split's logic can be altered in function of the regime. Okay, so this is for a possible practical application. If you, for instance, you can buy a hybrid car, and if you are running in a city, you can set your power split in order to behave better, in order to perform better in this more intermittent scenario. Or if you are traveling in a road, for instance, you can push a button, for instance, and set the power split for a better performance in this second scenario, in which intermittencies are much less pronounced. Okay. Yeah, and third, how the clutch is engaged strongly influences the starting of the movement for the internal combustion engine. I think I have yeah, I don't have a result here, but you can change. We can do this actually because I have the spreadsheet here. Let me just zoom here. Okay, I'm gonna show you the effect. Different gearing strategies, engaging strategies. Let me just try to put this in the. Yeah, okay. So I'm going to be more violent in engaging my clutch, okay? 0.1, okay? You see that the orange curve changes a lot, okay? It has a huge influence. If I am stupid with my gear, I can almost have the same as the hybrid car, okay? But this is not realistic. Okay, so that's the effect of how we engage the gear. Well, final conclusions. Yeah, go on.
Sorry, the gear system, is it manual or automatic?
This
Or it doesn't matter?
No, for this simulation it doesn't matter because it's always going to change so that you always have the maximum possible torque. Here, for instance, I can zoom in this curve here. Okay, if you see. So here we are starting, okay? When the torque starts to drop, it changes gear to the second gear, and we follow this path. Okay, if you don't change gear, for instance, if you don't, I have to, let me get my pen here. If you don't change gear, for instance, you can have this situation here. Okay, here, and then you change gear. Okay, oh, sorry, the color coincidentally is the same. Let me get a pen here. So if you don't change here at the proper time, I mean, you may have this situation here. Okay, now I'm going to zoom. No. Sorry, I messed up. I'm going back. Sorry. Yeah, so if you don't change gear at the proper moment, this moment here, you're going to have degradation in performance. Okay, so a manual operator can change at the proper moment. We do this roughly, but an automatic does exactly, it is programmed to change at this point, okay? So for our simulations, it doesn't matter because let's say a trained pilot can perform as an automatic, as exactly this way, okay? So it doesn't matter for our case. Okay, okay. Yeah, I was, no, where I am. Yeah. So back to our final conclusions here. Just to draw some conclusions from these simulations, the electric drive is better at lower speeds, although batteries are problematic as energy storage system. You saw this. A second important conclusion is that the internal combustion engine drive performs poorly at low speeds. It needs a clutch, it needs gears and so on, but liquid fuels are very good energy storage systems. Okay, and finally, hybrid drive combines synergistically both drives and also the best storage system. Okay, so the point is a hybrid car in a parallel configuration hybrid car combines the best of all these technologies, storage and drive. Okay, so but this configuration actually has two motors. Okay, two motors. And allow me to go back several slides. I forgot to mention one thing. I promised that I was going to explain why that BMW car had a very, yeah, here. Why the hybrid car had a small electric motor combined with a high power internal combustion engine. Because the electric motor is used only or basically to start the movement, to accelerate from 0 to 20 kilometers per hour or 30 kilometers per hour. Then the internal combustion engine takes most of the job of accelerating the car. And that is why you can have this configuration. Okay, we didn't do this simulation because we don't have anything to compare with this guy. You see that the torque here is fantastic, 210. Let's see the maximum torque. Remember, 210. Let's see our numbers. The maximum torque. Yeah, here. 100. Yeah. Yeah, not as low as that. 196 Newton meter. Okay, it's smaller. Yeah. This is comparable, but it's still smaller. Okay. Okay. So let me go back to the final conclusions. And well, the point is the hybrid vehicle combines the best qualities of two driving technologies and the best energy storage system. The problem related to hybrid cars is still its price. It's very costly. Okay, so that's it. I don't have anything else to say. Does anybody have a doubt or something? Okay, so thank you very much. See you next week.
Thank you so much, Seleghim. Appreciate it.
Thank you.
Thank you.
Thank you.